All right, so we're going to talk about things called sample spaces, different ways of actually representing your data. So a sample space is the set of all possible outcomes in a distribution, with a random variable, the numerical outcome of a random event. So you can either have it as discrete, which is something it represents a countable item, so it has a finite value and you can count it, or a continuous, where it can take on any value. There's an infinite number of values that you can pick from. So if we take a look at sort of identifying the difference between the two, it says identify the random variable in each distribution and classify it as discrete or continuous, and explain. So the number of songs that's found on a random selection of MP3 players. So the random variable X is the number of songs on any MP3 player in random selection, no particular order. But the number of songs, since everybody has a set number, it's countable. So you have a specific number associated, so X would be considered to be discrete. If we're talking about the exact distances of a sample of discus throws, the random variable X is the distance that's traveled for each of the throws, and the distances can be anywhere within a certain range. Therefore, X is continuous, because there's so many of them. So think of it that way. Now, probability distribution. For a particular random variable, it's a function that maps the sample space to the probabilities of the outcome. So there's lots of ways you could do it. You could use a table, an equation, or a graph. And we're going to use each of them, but the table and the graphs is going to come up first. So when we talk about probabilities of distribution, it could be determined theoretically or experimentally. It could be discrete or continuous. The probability of each value of X must be at least 0 and not greater than 1, because a probability always has to fall between 0 and 1. The sum of all the probabilities of the possible values of X must equal 1 in the end, so total. Theoretical probability distribution is based on what is expected to happen. So if we construct a theoretical probability distribution for the sum of the values on 2 dice, okay, so we have our sample space here. If we roll 2 dice, these are all the possible outcomes right here that you potentially could have. Say we have a red die and we have a white die. So if we construct ourselves a relative frequency table, these are the options we have in terms of sums, 2 all the way up to 12. You can't get 1 and you can't get anything higher than 12. So the frequency, or the number of times that we end up with getting a sum of 2, we only have one situation. That's 1 and 1. So there's 1. For 3, well, we can have 1 and 2 or 2 and 1. So there's 2. And you just work your way up on the actual chart and you figure out how many outcomes or how many possibilities you can have. And that's the frequency for that particular number. Now, on the whole entire chart itself, there are 36 squares. So there are 36 possible outcomes that you can have. So that is a sum of 36. So in terms of relative frequency, you do the frequency over the sum. It's a little hard to see it right here, but it's the frequency over the sum. Well, the frequency is 1. The sum is 36. So 1 over 36. And then you make that into a decimal. And you go down the line. So for 3, we had 2. So 2 over 36 is 1 over 18, or 0.056. And you go all the way down for all of the numbers, and you get the decimals that are associated with it. So that would be something called a frequency table. It's the frequency over the sum that you're working with. If you're then asked to graph that data, you're going to take those decimals. The number on the bottom is the sums that you end up with. So we'll count that as our X. And then on the left-hand side, that's our probability. So for 2 got us approximately right here, 0.028. Well, I'm approximating where it is, and I'm making a box. This is sort of like a bar graph a little bit. For 3 got us about 0.56. Make another line, and you go up, and you go up, and you go up. Now you're seeing sort of a nice little shape here. This is like a bell curve effect. Could it have that? Yes. Will it always have that? Not necessarily. Things might be slightly off, but definitely this is a perfect instance of something that does exhibit that bell-shaped curve for this. All right, let's try another one of these guys. So it says experimental probability distribution. It's the distribution of probabilities. It's estimated from experiments. So when you're conducting this type of distribution, you're going to use the frequency of occurrences of each observed value to compute its probability. Now, something to keep in mind, theoretical distributions may vary greatly from experimental. However, as the sample size increases, these variations in distribution should decrease. This is called the law of large numbers. So what that basically means is as the sample increases, we get closer to the theoretical probability value, which is what we're aiming for. All right, so we're going to sort of use a similar idea to what we just did with example 2. We're just going to talk about tallies here. So it says X represents the sum of the values found by rolling 2 dice. Okay. Construct a relative frequency table. We're going to roll 2 dice 100 times and use a random number generated to complete the simulation and create a random tally sheet. So key is it says 100 times. That's how many times that it was rolled. So that's a key number because that is the sum. Now, sum when I say total possible outcomes that we're working with here. So this is the tally sheet that we come up with. Similar to what we did before when we had the 2 dice, the red die and the white die with the chart. We look and we say, okay, well, what got me a sum of 2? Well, that's right here. My frequency is 2. So the sum is equal to 100. So for relative frequency, remember, relative frequency is the frequency over the sum. So 2 over 100, 0.02. 3, we had 5. So 5 over 100, 0.05. And you work your way all the way down the line. Okay? So now, last thing we're going to do is we're going to put on a chart. Same chart that we had before. So the sum is going to go on the bottom. And the probability is going to go on the left-hand side. And then you're going to make your little bars to make sure that they represent the proper amount that you need. And again,